Hello, everyone. Welcome back. Let's go on with birth and death processes and continuous time Markov chain stuff in general. Oops. Okay, so we are back. Last time we talked about birth processes. It was kind of a jumbled mess because for several reasons. One is I hadn't slept in a while, but also I think it's hard to talk about these without having multiple boards in front of us because there's so much stuff going on. Today we're going to talk about birth and death processes. We're going to skip the plain old death processes. And before we do that, I want to prove a very interesting theorem. And that is that if you have any time homogeneous continuous time Markov chain on a discrete state space, the inter-event times must be exponential, which may not be that much of a surprise because we need that lack of memory property to keep the Markov property going. But then again, it kind of maybe is a little surprising. So let me write this down. I'm going to let x of t be a continuous time Markov chain on a discrete state space that I'm going to call S. And so the conclusion here, the punchline is that the inter-arrival times must be exponential. So this is going to come into use today in birth and death processes because suddenly I'm going to be wanting some exponential random variables. So the inter-arrival times are exponential or must be exponential. So let's prove it. It's not that hard to prove, and it's not that long of a proof at all. It relies on the lack of memory property. And we did show earlier on in this class that the exponential distribution was the only distribution, the only continuous distribution with the lack of memory property. So if we take a continuous inter-arrival time here and can show that it satisfies lack of memory, it must be exponential. And again, just for the record, if you care about discrete time things, the geometric distribution is the only one with the lack of memory property in the discrete case. So for my proof, I'm going to suppose we're currently at some state I, and I guess by time homogeneity, I can make now time 0. So yeah, let's do that. I think that's going to be useful. So by the assumed time homogeneity, can assume that currently or now is time 0. And so I'm going to let not t, but t sub I be the time until the next event occurs, given the current state of the chain is I. So these exponentials could, and in fact will, depend on the current state of the process. They didn't for the simpler Poisson process, but they will for birth and death processes. So I'm going to let Ti be the time to the next transition when chain is at state I. And my claim is that this time is exponential, and here's some terminology for you. This Ti is usually referred to as a holding time. So you have a discrete state space and continuous time, and you don't have any weird rapid fire thing where we have to worry about a ton of things happening in a tiny, tiny infinitesimal time interval. Then you are moved to a state and you're there for a while, and then you move to a state and you're there for a while. So you hold in that state for a certain amount of time that we're calling Ti if you're in state I. And so, as I said, we need to show lack of memory. So we will show the lack of memory here. And this implies exponential, which we saw earlier in the course. So to do this, I'm going to take two time points, S and T, greater than or equal to 0. And we want to look at the probability that Ti, this holding time, is greater than S plus T, given that it's already greater than S. Ti greater than S. So what does this mean in terms of the Markov chain? I'm assuming that we started in state I, and by time homogeneity, I'm assuming that we started at time 0. So this stuff can be translated to the Markov chain by saying, this is the probability that x of, I need another time index, I usually go for u next, that x of u is I for all 0 less than or equal to u less than or equal to s plus t, given that x of u is I for all 0 less than or equal to u less than or equal to s. That is equivalent to the line above, and let me know if you don't think so. All right.
All right.
So if I'm already given that we're in state I all the way up to time s, then computing the probability that we're in state I for all times up to time s plus t really just means that we need to compute the probability that we stay in state I from time s to s plus t. So this is equivalent to the probability that our Markov chain is in state I for all u between, let's see, strictly greater than s and less than or equal to s plus t, given the same stuff as before. And the reason that's true is because we already know we're at state I for the first part of that longer time interval. Okay, so now I'm going to use the Markov property because I want to get rid of this for all stuff over here. So by the Markov property, I'm going to look at the last point given. So this is the probability that x of u is I for all for all u greater than s less than or equal to s plus t. And then by the Markov property, since I know that x of u is I for all u between 0 and s, I'm just going to take the fact that x of s is I, the last one, the last observed one. So stop me if any of this is not making sense. Okay, so let's shift everything using time homogeneity. I'm going to put TH for time homogeneity. I'm going to shift S down to 0. And this becomes the probability that x of u is I for all 0 less than u. I left off my u in the line above. There's a u in there. Less than or equal to t, given x0 is I. And now we're there because this is precisely the probability that t sub I is greater than t, because we started at state I and we stayed in state I for all times up to t. So this precludes us like moving from I to j and then moving back to I. If we stayed at state I for all of these, then the first, the holding time in state I is, you know what, we could have actually moved from I, we could have stayed at I. So we're still there. Oh, yeah, what happens if we stayed at I? So I was going to try to argue that if we started at I and we're still in state I for all continuous time up to some time t, that means the time to stay in I is at least t. I want to be the next transition, not only from state I, because that could technically be a transition from I to I want it to be the time to the next transition away from state I. So like a birth, we go up by 1, or a death, we go down by 1. So I'll fix that up in the note. So it's not just the next state, it's the next time you move away from I. So then I don't have this problem. Well, maybe I do. I'll look at this a little more carefully before I write it up. But that's the idea. So any questions? Okay, I can't remember because these classes all blend together, if we ever talked about the minimum of exponentials in this class. I kind of think we did at one point. So I want to use the fact that the minimum of NIID exponentials with rate lambda is a new exponential with rate n lambda. So if we have x1 through xn IID exponential with rate lambda, then the minimum of x1 through xn is exponential with rate n lambda. Does anyone know if I did that in this class?
Yeah, I think you did.
Okay, thank you. If I were to wanted to do this again, I would call this like YN, and then I would go for the CDF and start writing it out. So I think I did too, but I'll add this to the notes as well. So I just want to use this fact and move on. And so we just showed that for a continuous time Markov process on a discrete space, such as a birth process, the time to the next event is always exponential. And we saw that for a birth process, when we're at state I or population size I, um, the rate of the next transition, that is how I have to save that other proof, transition away from I. The rate of the next transition away from I, in this case for a birth process up to I+1, we saw that we called it lambda sub I. And we saw last time that this was equal to I times lambda, where lambda was given as the, yeah, I was hoping this would be better than the last day. So this is, well, this is the Yule process, the birth process, the one we talked about. It's just not, it's the linear birth process. It's not a general birth process because we have other birth rates. But here is my point. This is the probability that if you're currently at a population size I, this is the probability that in some small interval h units of time later, you have increased by 1. This is lambda IH plus little o of h. That's our definition of the birth process. And we saw that in the Yule process or linear birth process, that lambda I was I times lambda. And so here's what you're seeing. We have I individuals all giving birth to some offspring with rate lambda. And this is I just say, the next transition. You've got I individuals, they're all racing to give birth with exponential clocks. And the next transition is going to be the minimum of I exponentials with rate lambda, which makes it exponential with rate I lambda. And so now that we know this fact that the times were exponential, maybe we could have maybe guessed that. But at least it's in line with what we know about the minimum of exponentials. So yay. Right. Okay. So let's put some death into the mix. I'm not doing this as jovially as usual, given our current circumstances. But we have to talk about birth and death processes. So this is just where we're going to have xt be a population size at time t. And we're going to allow it to go up and then down and then up and then maybe down twice and up 3 times. And so basically we're introducing departures to the system. And so here is the definition. We say that the process x of t is a birth and death process if the xt is a Markov process on the same state space, 0, 1, 2 on up, is a Markov process on 0, 1, 2 on up. And so we're going to allow us to go up by 1, down by 1, stay where we are, and then we're going to show, well, the definition is going to say with some negligible probability, we can make a jump up or down of size 2 or 3. So, and for a little h going down to 0, the probability that x of t plus h minus x of t is k, given x at time t is I. So this is going to be like a lambda I h plus little o of h if k is 1. That would be an increase by 1. And it's going to be some mu I h plus little o of h if k is minus 1. And we called the lambda I birth rates, and these mu i's are known as death rates. And this is really, really standard notation. People use the lambdas and mu's here. We have that with probability little o of h, we can move. So I'm going to say that if the absolute value is greater than or equal to 2, that's really negligible. This is part of the definition. So there's no why is that true. And then the final one, we want these all to add up to 1. And doing our little o magic, we get 1 minus lambda I plus mu I in parentheses h plus little o of h if k is 0. Because we just showed this thing about exponential inter-event times, we now can use things we've already done, like for our bug jumping processes. I could ask a question like, what is the probability the next event is a birth, given you're at state I? And I'll write this down eventually more formally, but we know that that's the birth rate over the total rate of moving away from I. Like we have these kinds of results that we saw back with the bugs and the Poisson processes. But yeah, I'll say that later. We really, I guess I'll do part of one example. These get tedious. I actually love to do them. I can sit and write out these little equations for hours, but I have a feeling I would then look up and find I'm the only one in the room. So here's an example. I've got a population in which no individual can give birth. I've got a death rate of mu per individual. And this means, when that's being written, exactly what it meant with the birth rate last time. So death rate of mu per individual. And the definition of this is the probability of a death, a single death of an individual in any interval. So the probability, I don't want to say a death, because that's the whole process. The probability an individual dies in any time interval that looks like a t to t plus h, that this is proportional to the length of the time interval with proportionality constant mu, so mu h plus little o of h. That is just what is meant by saying the death rate per individual or the birth rate per individual. So this process isn't going to be very interesting if no one's being born. So I'm going to put some immigration here. And so I'm going to say people or individuals immigrate in according to a Poisson process with rate lambda. I wanted to show you Zuko today, but he's shedding. He's not happy. But he's like, he didn't grow at all for a month because he didn't eat, but he doubled in size this week. Pretty cool. Immigrate into the population according to a Poisson process with rate lambda. And this is going to be independently of what's going on in the population. In the population. Okay, so I want to show this is a birth and death process and give the birth and death parameters. I'm just going to show like one of those computations. Show this is a, let's say, argue that this is a birth and death process and give the birth and death parameters. And I never wrote out the death parameters. I did say that mu I are the death parameters, but I probably should have taken the time to write mu sub I is the rate of death when the population is currently at size I. The birth and death process and give the birth and death parameters. So I'm just going to argue it kind of loosely here. This is even kind of more Markov than a Markov process because people immigrate in without even looking at the current population size. Well, actually, they die according to the population size. But you can see that if you have a given, so take any time, any continuous point of time, fix it, look at your population size. If it's I, you know where you're going to go next and when you're going to do it. You're going to start an exponential clock. You're really going to look at the minimum of an exponential for the births and the exponential for the deaths. And then once that clock runs out, you're going to increase the population or decrease it with the right probability. But none of this needs the further back history of the process. So clearly it's Markov. Okay, so let's do the work of, I just want to pick one of these to show. In general, you need to show 3 and then the other one's locked in. And at the beginning of doing stuff like this in homework, and I'm going to put out an assignment today, but it's not to be handed in, it's just for practice. If you have time, I would do all 4 just as a check, make sure they do add up to 1. Not with this particular problem because this is ridiculously long. So I'm going to let x of t be, did I already write that? I did not. The population size at time t. So we want to look at things like, I'm going to let a little h go down to 0 and consider the increment, the probability that x at time t plus h minus x at time t is, let's say, 1, given x at time t is I. So this means that this is the probability of exactly 1 immigration. So I'm going to start writing I for immigration. This is really a lot to write down. And 0 births or 0 immigration and 1 birth. Yeah. Given that our current population size is I. That makes sense because I know I got really sloppy all of a sudden. So we can increase by 1 in one of 2 ways. Also, actually, I need to say plus a little o of h term. Now, I just sort of say that, but you can show that because you can imagine since we go up and down, that increasing the population size by 1 could actually mean we had 2 births and 1 death. But in this case, the births are immigration, and the immigration is a Poisson process in this example. And the probability of having 2 arrivals in a Poisson process in a tiny interval is little o of h. So we actually have formal arguments to get to this. And that would be saying, in this case, the Poisson process cannot have 2 arrivals or more in a tiny, tiny time interval. And obviously, we can't have 8 births and 7 deaths, all the other combinations. Okay, so these are disjoint events. So I'm going to write this as the first probability plus, so this is at the or, the second probability And then like the first one consists of one immigration and, oh, no, there's no birth in here. I have immigration and death. So these B's should be D's. Zero deaths, one death. But because we were given in this well-formed example that the births and deaths are independent, I keep saying births and deaths because it's a birth and death process, but the immigrations and deaths are independent, we get in both cases to take this intersection and break it up into a product. So this is going to be the probability of one immigration. All of this is conditional on xt equals I. I'm kind of sick of writing that. And I kind of want to write the p sub I here, but that is usually time 0. But then again, it doesn't matter because this is time homogeneous. So I'm just going to keep this on the side. So all of the probabilities I'm about to write are conditional on the current population size being I. So this is the probability of one immigration times the probability, so this is by independence, of 0 deaths, or the disjoint event that we had exactly 0 immigrants come into the population, and independently, we had 1 death. And then that whole thing is plus the little o of h. And is everybody with me?
Just a quick question.
Yeah.
So we're trying to see if our population increases by 1 in a very small time interval, right?
Mm-hmm.
And our first probability says we have 1 incoming and no deaths. That increases by 1, right?
Yeah.
But our second one
Oh
says we have,
gosh. Yeah. Yeah, I'm thinking of, yeah, that's not right. I'm thinking about, yeah, I'm thinking about the thank you so much for catching that. I'm thinking about the transition to 0. So if this thing up here was 0, then I could have 0 immigration and 0 deaths, or I can have 1 immigration and 1 death. And so you're absolutely right. I'm doing this completely wrong. The only way we can, if we don't have any immigration and have 1 death, then obviously the population size is decreasing by 1, not increasing by 1. Oh, I'm so sorry. I'm going to cross this out rather than erase so you can see exactly where things went. This is not part of this equation. And that means that this second thing is not part of the equation. And that means that this part is not part of the equation. So thank you so much. Okay, let me try to clean this up. The probability that the population size at time t plus h minus the population size at time t is 1, given we started with a population size of I. This has come down to the probability of 1 immigration, given the population size is I, times the probability of 0 deaths, given the population size is I, plus the little o of h, which wraps up all the other stuff that we didn't get 8 arrivals and 7 departures. So for this first one, the immigration process is a Poisson process. And this is, you know, I tried to write it out more neatly, but I did leave out that this is an immigration in the time interval from t to t plus h. And this other one is a death in that time interval. So being a Poisson process, we have a little interval of length h. So the number of arrivals or immigrations here is Poisson. Did I give it a parameter? Hopefully I called it lambda. Yeah, is Poisson with rate lambda h. That's the probability of having 1 Poisson arrival in there. So we get e to the minus lambda h to the 1 over 1 factorial. And then the other one for the 0 deaths. So we have the death rate per individual. Oh no, I've been missing chats again. We have the death rate per individual. All right, that was a while ago. I don't know if this will make sense. Oh yeah, you asked the same question that was asked and answered, sorry. I think I'm all caught up. Okay, so if there's I in the population, we have to choose 0 to depart. That's I choose 0. The probability any one of them departs in a tiny time interval of length h is mu h plus little o of h. We get that to the 0. Then we have the rest of the probability, 1 minus mu h plus little o of h, and we get that to the I minus 0, and then the little o of h on the end. Okay, so this first term, I've got a lambda h, and I think we've already talked about this term. The e, I would look at the Taylor series expansion. And say all of this stuff is little o of h. So I'm going to rewrite the e term up here as 1 minus lambda h plus little o of h. Then the I term, the I choose 0 is 1. So that's 1, that's 1. And we get this other guy, 1 minus mu h plus little o of h, the I, plus little o of h. So in problem 2 in your homework, I'm going to now use the part C of problem 2, which I did say last time was a direct result of A and B. But after someone asked me a question in my office hour, I realized it was not a direct result. But if you did that already because I gave that hint, then that's fine. But really, I need to show what this simplifies to by applying the binomial theorem to this guy plus the little o of h. But we do know that this is, well, this is lambda h, 1 minus lambda h plus little o of h. And then this is 1 minus I mu h plus little o of h. So this is 2C on homework 7. And in the notes that just went out, the notes that I posted this morning, which aren't for today, they're for last time, the birth processes, I do have those 3 facts listed and some space where I'm going to put those proofs in once your homework's been turned in. Okay, what do we have? We multiply things out. What survives is really all you need to know. We have the lambda h times 1, and that is not little o of h. So that's something we have to account for. We have the lambda h times, oh, and times other things, but the lambda h times lambda h is little o of h. The lambda h times o of h is little o of h. So maybe first I should rewrite this as lambda h plus little o of h. That little o of h came from this one and this term, and that's it. And then the other part of this is just sitting there. And now if we multiply this out, the very first term survives because the little o of h terms are powers of h2 and higher. So I do get the lambda h, and then I get an h squared term, which is little o of h. And then I get a little o of h times an h term, still little o of h. And a little o of h times 1 is still little o of h. And a little o of h times something with an h up there is still little o of h. And yeah, everything is little o of hing away. The only thing that survives this is lambda h. Well, that makes sense because, yeah, I meant to do the other example where we had one immigrant and 1 death, or the other way around. We already kind of knew what was coming here if I knew what question I was answering. We've got an arrival process that is Poisson. They're coming in at a constant rate. This is exactly what we saw for an increase of 1 unit in a Poisson process. So, questions? All right. All right, so we could do this one problem for 2 classes. We can go through all the cases, but I'm not going to do it. I did write up many more of these cases. I think I finally said etc., but I wrote up at least 3 of the cases for this problem. And you might say, aren't there only 3 cases plus the 4th one that's locked in? But I actually did talk about all the other things like 5 arrivals and 4 departures. And so I went through a lot of cases for this problem in the notes that I am going to post today. All right, I love birth and death processes. They're really tedious, obviously, but I just find it relaxing to sit there and write little O equations for days on end. But let's talk about something else. In general, in continuous time Markov chains, we are talking about some rates of transitions, which are really infinitesimal rates of probability transitions. So let's look at, let me call this part infinitesimal transition probabilities. In general, for a birth and death process, we can move from some state I to some state J in a tiny h units of time with the following probabilities. I've got a P sub ij. Our new continuous time notation says, put the time in here, usually a t, but right now I'm going to talk about the little h. So this is lambda ih plus little o of h. If j is, so I'm writing it different, right? This is not in terms of an increment. This is a birth, so j has to be I plus 1. And it's mu ih plus little o of h. If j is I minus 1. And it's 1 minus lambda I plus mu I h plus little o of h. If j is equal to I, and it's little o of h otherwise. So h is small and going down to 0 for this statement. So I want to write this a little more compactly. I'm going to write this like this. The probability of going from I to j in some tiny interval of time of length h, I can write this as a delta ij, where there's more, but I want to get this in already. Delta ij is going to be 1 if j is equal to I, and 0 if j does not equal I, plus something that I'm going to call qij times h, plus something that is little o of h. So here is up here is the case where j is I, and in that case, I get a 1 out front, which is represented by this delta, which is 1 when j is I, and the others don't have 1s. And I'm defining at this point the qij's to be the coefficients on the h's. So let me write that down. Oops. And qij's are the coefficients on the h in this expression. We call these QIJs the rates of transition, some birth rates, some death rates, and this weird negative sum of rates. Like, what does that even mean? We're getting to that. So store the rates, the QIJ, we store this in a matrix that we call usually Q. And so the ijth entry is little q sub ij. And this is known as a generator matrix in stochastic processes and Markov chains. Generator matrix. This is going to be what we're going to work with to find stationary distributions. We haven't even defined that yet for the continuous time case, but we will. We can't use our P matrix because now it's a P of T, and T is changing. And so that's too hard to organize the probability of transition in T units of time for various values of T. Okay, so that's just notation. Is everybody okay with how I rewrote this like this? Don't have to say anything. Just speak up if. All right. Okay, so last thing I can fit in today is that, so I now have this expression. The probability of going from I to j in h units of time is a delta ij plus a qij h plus a little o of h. And I want to solve for the qij's. So the qij's are the pij of h minus delta ij plus little o of h. And then I'm going to divide through by the h and kind of separate these. They really all go on over one. It's really one fraction, and then I separate them. And note that the delta ij, which is 1 when j is I and 0 otherwise, this is exactly the same thing as pij of 0, because you can't move from state I to state j in 0 units of time unless j is I. And so if I write it that way, you're seeing something that looks like a derivative. So as a final move today, I'm going to let h go down to 0 on both sides, meaning over here where there's no h and over here. So my qij is not changing in terms of taking the limit on the left side. So we get qij, and then on the right side, this is going to go to 0, and this other thing is going to go to the derivative, and yes, technically a right derivative, but it's going to go to the derivative of the transition probability at time 0. Yeah, and that's it, like plus 0. So that's a prime. And so that's why it makes sense to call this a rate, you know. It is the instantaneous transition probability moving away from I to state j. It's a derivative. Does that make sense?
How do we know that the O of H over H goes to 0?
Yeah, that's how we defined a little o of h function. It's a function such that if you divide by h, it will go to 0. But warning, little o of h divided by h is not necessarily little o of h, but by definition, a little o of h divided by h does go to 0.
Gotcha. Thanks.
So, I'm not really out of time, but we're supposed to be like chilling and spring pausing, and I wanted to always end a little early. Let me just end this with our generator matrix is going to be our transition matrix at time 0 with a prime here, where this prime is the element-wise derivatives. And that's evaluated at 0. We're going to see that unlike a probability transition matrix, the rows of Q are not going to add up to 1. We're going to see that they must add up to 0, and they will define the whole chain for us. And then we're going to write down a stationary equation. We're going to define pi, and it's not going to be like pi equals pi times p. It's going to be an equation involving Q, because p is too hard to work with because you have to change the matrix for every time t you want to put in there. Yeah, the elements of p are functions of t. We are talking time homogeneous, so it doesn't matter where you are, but the p sub ij of t is the probability of moving from I to j in t units of time. And it doesn't matter where that time starts. But yeah, they are functions. And we have a matrix, you know, I've learned my lesson. I'm never going to say in this class again, if I teach it again, that you don't need to know differential equations, because I have one more coming up, and it's a matrix differential equation. That will be next time on Markov chains. So thank you. I'm done.